Okay, so I want to finish up that proof today on um, that if you want to actually form a orthogonal, that if you want to basically diagonalize your any type of symmetric matrix, that basically use an orthogonal matrix, and your orthogonal matrix components are going to be composed basically of the eigenvalue of the matrix. So we did the following. Said so yesterday we proved that if uh, A is a symmetric matrix. Were we calling A? We're calling O, weren't we?
Yeah.
We're calling O. Okay. Is a symmetric matrix. Its eigenvectors are orthogonal. You know what does that mean? What does it mean to be orthogonal eigenvectors?
Perpendicular.
Okay, meaning that in terms of matrices, it would be what?
It's transpose.
The transpose. So in other words, if we have said that if O acts on this VI, we get lambda I VI. So why did we call that an eigenvector? Because what does it mean to be an eigenvector? You do something to something and
Times a constant.
you get it back in terms of constant. So this is the eigenvector here, and this is your eigenvalue. So that's one of them. Then we had another one that was sustained. We proved that you have this combination here. So this is orthogonality. Orthogonal vectors. Eigenvectors.
Where I is different than J.
Where I is not equal to J. Okay. If so often, meaning almost every single time, the eigenvectors are normalized. Such that. So what does it think? What do you think it means to normalize the eigenvector?
Something times something equal 1.
So I want VI, then VI transpose. So I'm taking the eigenvector, then I'm multiplying by its transpose. And I want to set this if it's normalized. So if I put this condition and this condition together, which one do we have? I can then write this. That's going to be your fancy Schmidt who writing this. Hey, it's 0 if I does not equal J. Hey, if I equals J, then it's 1. That's everybody. So that's the condition we're going to have here. Okay. Again, when you take quantum mechanics, what you're going to find out is that you're actually going to do the diagrams. You're going to basically say that your eigenvector should multiply by the dagger of another eigenvector. What's dagger? What two things?
Transpose and complex.
Transpose followed by the complex conjugate. That'll be 0. In this case, then you're going to say VI dagger, VI equals to 1. Then you're going to have VJ dagger, VI equals delta G. That's what you're going to have in quantum mechanics. Okay. That makes sense? And then again, what you're going to have in this case here, you're not going to have a symmetric. What you're going to have is that you're going to have Hermitian. And Hermitian means, what does Hermitian mean? Again, this is not, I'll never ask you this in this course, but we're so close to it, you might as well, I might as well prep you for it.
Energy. The polar. Is it when inverse and is the trans?
Okay, so this is an assumption. So next semester. Quantum mechanics. You will have Hermitian matrices. A Hermitian matrix means O dagger. Maybe the dagger is composed of two things. It's composed of the transpose followed by the complex conjugate, or by, it doesn't matter which of this independently or do. Okay, this equals, oh. That's remission.
So it's quantum mechanical, symmetric.
Because and the reason is the quantum mechanical analog of symmetric matrix.
The dagger.
The dagger is going to be the transpose of the matrix, followed by the complex conjugate, or the other order, doesn't matter, because we'll depend on. But this equals the original thing, and you call it permission. It's a remission matrix. If you ever go to a talk and somebody gives, you have no idea what question to ask, you say, excuse me, is that permission? You know, you might get one or two answers like, well, why the hell would I show it to you if it wasn't permission? You might get like a duh response. Or you might get a where people think it was proof. What I'm doing. Okay.
So is that the symbol of that plus?
It's a dash. It's not a plus, it's a dash. It looks more like a plus. It looks like that,
Alright.
but it's always called dagger. Which is the quantum mechanical analog of a symmetric matrix. And let's just continue with this. If O dagger equals its inverse, then the matrix is unity. Maybe I'll have you work this out as a homework, because it's not that hard, you just do one thing. I'm just making an aside. The eigenvalues of any remission matrix are here. Okay. And again, for those of you who had modern, why is that important? What do the eigenvalues end up becoming?
The values
What kind of values?
along the
Or just, I mean, just in terms of practical purposes. Okay, the eigenvalues are basically your measured quantities. And when you measured quantities, so you ever get an I when you measure something? No, that usually doesn't happen. It's imaginary. You know, that doesn't happen. You always get a real number. Okay. And since the eigenvalues are going to be what you measure here, they have to be real. Yeah. What's the proof of that? Proof of this? Let VI be the eigen vector of permission matrix. Oh. So what does this mean? That means with O, X on VI, which is the set equivalent, if it's an eigenvector. And the I, VI. Okay. Prove it now. Prove that this has been zero. What might we do to both sides before we tinker with it? You're gonna multiply both sides by VI transpose. Multiply both sides by VI transpose. This is just a number. Now what are you gonna do? We haven't made use of the fact that this is remission. Again, I'm giving you a little prep work for one next lesson. You're getting an assist.
Take the dagger from both.
Take the dagger on both sides. We're really called Macbeth again. Okay, so Oh, let me rephrase this. The transpose here is not really transpose, it's really a multiple side pointed dagger. Sorry about that. So used to what we're doing here. Okay, what happened, what did we say, dagger is again? Transpose, complex conjugate. So what's gonna happen then with the transpose part of this here?
Switch the order.
Switch the order and take the transpose thing. And then what do we have to do, since it's a dagger, we also have to take the complex conjugate. So it's the same thing as taking the dagger of everything here and then flipping the order. So this could become over here. This is dagger, but it's really this one over here. This now becomes O dagger. What happens if I dagger a dagger?
Dagger goes away.
Yeah, I under dagger it. Okay. Because it's a complex conjugate followed by a complex conjugate undoes that part. But then a transpose followed by a transpose undoes that. So this guy then comes over here. Equals. Now what happens if I need to got my dagger here? What happens if I dagger a constant? I just get the complex conjugate because it's just a number. So if I take the transpose, it just is that same number, right? Because it's a 1 by 1 matrix, it's just a number. So this should become the lambda star. And then again, these orders get switched. Okay. Now this is permission, so what does this equal here?
Just,
Oh, this is just O. What is that? That's no X on VI
And VI.
and I VI. With both on I. This is not zero because it's basically the quantum and one without product. So this gives me lambda I. Was lambda I star. When is a constant equal to its complex conjugate? Only if.
Just real.
Only if it's real. Therefore, lambda I is right. Okay, I also have no ulterior motive for doing this as well. So we're working on the homework where I'm going to have you basically do the quantum analog of the proofs I'm doing today. So because it's actually just a good exercise. But then also it'll get you ready for one. And also we'll make use of this when we do for those taking computational physics, we're going to use some of these ideas too. So I'm double dipping. We're tripling. Questions? Okay. So now we can do the proof then. So the claim is the matrix that if we write the matrix A as, and instead of, I'm going to do the transpose here, not the A, but the transpose. If I put my vectors here, so this is my first eigenvector with my second eigenvector, and these are normalized. And here's my third eigenvector. If I put them here, this matrix here is going to basically, this will diagonalize the matrix. So if I have this, then A times O times A transpose is a diagonal matrix with the eigen values of O along now. Okay, so the claim is that if I do this, I'm gonna have some new matrix here. I'm gonna call it this O, not for the primary term. And this O prime is gonna be basically lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. What do you think is gonna happen in quantum mechanics? What do you think that becomes?
Transpose, just go to the dagger.
Done. So I want to do the proof of this here. And the proof is, okay, I think mathematician would hate my proof. This is going to be basically a picture proof. But to me, I think this actually is the most coherent way to actually see what's going on. The mathematician would probably hate it. You know, I think it's actually a good proof. So it's going to be really a proof by construction. So we will prove this. Thing by construction. Meaning we're going to basically set this up and see that it works. Okay, I think that's the easiest thing to do. So if by construction this A is again, this is V1, V2, V3. If it's that, then what is A?
E1.
Yeah, it's going to have to be, this is going to have to be basically V1 transpose here, V2 transpose here, V3 transpose here. That's what it has to be. So I'm going to set up that matrix. I'm going to set up this combination here, and then you'll see, and you're going to say, "Oh, of course, this has to be the case." Just so you know, the number of times you have to do this in life is phenomenal. Okay, if there were a top 5, basically, if there were a top 5 or 6, top 10, you know, the top 6 math techniques that you use. Okay. Probably number 5 is setting the determinant of, you know what, of singular matrix is 0 to get, you know, the non-trivial solutions. And probably the next one here would be, you know, with Vapin. With this equaling would be one of these. Okay. That's used absolutely everywhere. Okay, so let's just set this up. So A, O, A transpose. So what is this going to be? This is going to be basically, I'm just going to have my A here initially. Here's my O. And then I'm going to put in my A transpose as this guy over here. Now, see, here's my O. And I have my transpose over here. So this is my 1, V2, V3. If I would say work this, it's like here's what you transpose. If I say multiply this by these, what would you do? Right, I do for this guy here, right? And then for this one over here, then I do, you know, I do this type of stuff here. When this matrix here acts on here, what happens?
Yeah, I do.
You know, when this matrix here acts on this guy here, it's an eigenvector. So I get back this whole matrix here multiplied by
I get
lambda one, right? So what's gonna happen here? That result here, I'm gonna write this as just lambda one times v times your v vector here. That makes sense? Well, what happens when I do this one here? When this matrix here, oh, X on my V2, what is that gonna be?
lambda two.
Lambda two times your V2. This one here is gonna be the lambda two, your V2 like that. And likewise for this one here. Lambda three, those are the previous three and this. The mathematician would probably hate this notation here, and not incorrectly, but it's, I think it shows you exactly what's occurring. Does that make sense? And I can see exactly what the rest of this is gonna work. So we're going to construct this thing over here. Well, what is my A? My A is going to be this guy here. Here, and then this guy here is that mess over here. And how do you multiply these? I do dun 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 dun. And what would that give me? Well, lambda one's a constant, so I can pull this out. What do I know about the V1 transpose times V1? That's been normalized to one. So this first element is
Lambda one.
lambda one. Suppose now I want this element here. Now I do dun 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 dun. Well, I choose a constant. I can pull this out. What do you know about V1 transpose times V2? Because they are orthogonal. So this has to be zero. Likewise for the other one, zero. And what happens in here? Well, I take this one, dun, 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 here. Well, that has to equal zero. But when I do this one, dun, 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 I get
Lambda two.
lambda two. So then I get lambda two, zero, and then likewise for the other. Okay, so a mathematician would most likely hate this. I think it's actually positive and really good. Okay, that makes sense. Questions? So, if you want to actually switch the coordinates here, basically this is going to become the rotation matrix. So remember what we have here. Oh, and also what do we know about? So what do we know about then? This A and the A transpose. The A and the A transpose are. What do you know about this A? And A transpose. What does that have to do?
So. I can't see one.
The identity matrix. Okay, it's going to be this. So the A transpose is really the what?
A inverse.
This is the inverse. So that matrix A is the transpose equals the inverse, then it is an orthogonal matrix. Therefore, A is an orthogonal matrix. So anytime you have a symmetric matrix, you can always diagonalize it with an orthogonal transformation. So any symmetric matrix. And you know, again, the number of times you have to use this in life is phenomenal. Okay. So any symmetric matrix can be diagonalized with an orthogonal matrix. Okay. So the way the way we use this again, let's just go through and make sure we understand how we're using this. So the way we're using this is that we have this equation here. What did we do with this? You multiply both sides by A. This is our rotation matrix. This is the rotation matrix. What do we insert in here? One over 3 most important math techniques, 4 most important math techniques.
Times 1 by 1.
We put in 1 in a clever fashion, so we put our 1 in here. And how do we write 1?
Identity matrix.
Okay, this identity matrix, how do we write it? There's a fancy way.
A times A transpose.
We want to go the other way. A transpose times A.
Oh,
We're going to do this. Why do we do this? Because this is nothing but Ax in here, that's just rotating the vector, so we call that
L prime.
L prime. That becomes our buddy. Am I still there? I am. So this is nothing but a rotated vector, so this is our L prime. A acting on omega does what then?
Omega prime.
That rotates that column, that's fine. But hey, this I here is not a vector, it's a second rank tensor. How do second rank tensors transform? Like this. So that becomes our by well from here, because this is a second rank tensor. This is how second rank tensors transform as matrices under rotation. Now, what's going to happen in general relativity? We're going to go to a 4x4 matrix. And what they're going to be is that instead of basically rotating, we're going to do a Lorentz transformation. What's going to happen here is that these are going to be Lorentz transformations. These are going to become full vectors. Okay. And so what's going to happen here is that we're then going to talk about Lorentz scalars, Lorentz vectors, Lorentz tensors, things like this. We're going to find out that the electric and magnetic field are nothing but second rank Lorentz tensors. So if I want to figure out how electromagnetic fields transform, what I'm going to do is I'm going to do this operation here. And it is easily the most efficient way to actually draw these equations. If you don't use that method, good luck. It's absolutely pathological. Yeah, this you end up having to multiply 3 4x4 matrices, but you just have to be careful. It ain't hard. The other way, it's just pathological. But if you make use of the transformation properties of it, easy peasy. And we'll see that. And then when you take the second semester of advanced CNN, you'll see it again. No sense. Questions? Okay, just another little preview. Don't write this down. So when you do the Einstein equations, the Einstein equations are really just. I won't bring the bars here. Well, we have two indices here because basically this and this, and this, these are second rank Lorentz tensors. So this is really a 4x4, and this is really the 4x4s. Okay, that's really what we don't know right now. Okay. So why are they called? These are called the Einstein equations. Why are they called the Einstein equations? Because those equations have it's a 4x4, so there are multiple equations. So it's not for the Einstein equation, it's Einstein equations. Yes.
So if you had like a third rank tensor, would you have to have a three-dimensional?
That'd be a three-dimensional range. So it'd be like I don't know. You can think about one-dimensional matrix as being like a vertical filing cabinet here. a two-dimensional, just a regular vector, tensor rank one is a vertical filing cabinet where you have drawers like this. Second rank tensor would be basically a filing cabinet like this, where I have drawers like this, drawers like this, okay? Then a three-dimensional one would be a big block. You can't really, or somehow you could reach it and pull another single dimension like that. And then you extend it in the fourth and fifth and all these.
Is the I prime diagonalized? by
Yep, because what we're gonna do is that we're gonna use, actually, we're gonna construct the A's as the eigenvectors of this. So right now, this doesn't have to be, this could be anything.
Okay, so you.
However, exactly, if I construct this A with those eigenvectors, then this is gonna be an eigen. And that's what we're gonna do, because this will make life a lot easier. That makes sense? Questions? Okay, I want to get the kinetic energy in here, then we're gonna take, we're gonna skip this for a while, then come back to it. There's a reason why we have to skip, because we need something from a rotating coordinate frame. So you're gonna say, what happens if you do, well, actually, let me just set this up so you can see something here. We live on the Earth, okay, and imagine that the Earth rotates, okay? So, suppose, somebody in, let's say, South Carolina launches a missile at us. Oh no. And here's the United States. It turns out it looks exactly like. Is that a picture from National Geographic? It looks exactly like one. So South Carolina is going to launch a missile at us. Here we are. They launch a missile at us. What's going to happen? So they aim their missile at Richard, Alfred. What's going to happen to their missile? Okay. What I'm going to try to convince you is that if we're here, we're going to see that missile go like that. We're going to go, ha, losers, you can't even fire a missile. Okay. Why does it do that?
Is the
It's going to be because the Earth rotates. If the Earth didn't rotate, it would go and actually hit us here. Now, what would we have to say in our case here? When we see something move like this for no apparent reason, we would have to say there's a force acting. So we would say, oh, there has to be some magic force deflecting this object like this. We're going to call it the Coriolis force. Turns out there is no such thing as a Coriolis force. It's a fake force. And the reason, but it comes across looking like a real force. And the reason why it's here is because we live on a rotating frame. And so what we want to do is I want to couple basically a rotating frame with these ideas here. And then we're going to get something called the Euler equations. We're fleeing together. So I want to calculate the kinetic energy for a rotating object. Then I want to go and talk about what happens if you have a rotating frame. And then it turns out, this is really important if you're doing any type of weather systems and stuff like this. This is the only way you can really understand weather systems. You have to account for that. Talk a little bit about the general circulation of the atmosphere. For those of you who had the planetary science course, did you do anything with Coriolis forces and stuff like that?
We talked about it.
Okay, we're gonna derive them. Okay, we're gonna calculate the speed for a hurricane as well. We have to make a couple simplifications, otherwise it gets path 11. Because these equations become three-dimensional really fast in a bad way. Well, it's a good way to. But we can actually get the speeds pretty easy. And then it turns out also with planets we can get something called a Hadley cell, which is going to talk about general circulation of the atmosphere. I want to show you what a Hadley cell is. It's going to come from these ideas. Okay, so but before we get that, kinetic energy of a rotating object. So let's ask, what is a kinetic energy of a rotating object? So here's my little object. X, Y, Z. I'm rotating along this axis here. Here's my omega axis. What I'm going to try to convince you of is that kinetic energy is going to be 1/2 omega transpose times L. Okay, or 1/2 omega transpose I omega. In this form here, what does it look like from first semester physics? Normally, if you have a rotating object, what do you learn in general physics? Rotational kinetic energy is given by
1/2
I. I.
Omega squared.
Omega. Okay, so it's really, it is that equation, except remember what happens in general physics. You're just dealing with those diagonal terms, because you're basically rotating around the x, y, and z axis perfectly. You're not doing a general thing, so this is what you're doing. Proof. Okay, and you are pros at this, you tell me exactly how to do this. And there you hint, it's exactly how it got out.
T equals 1/2 MB squared for some DM.
And we're done. That's exactly what you do. You have to treat that object as
Reflection.
a collection of points. We only have one kinetic energy expression, that's 1/2 MB squared. So we're gonna write 1/2 MB squared for a tiny little DM. Be careful of it. Add them all up and Shazam, we got ourselves the angular momentum amount. Okay, so treat the object as a collection of point guesses. Yeah. So here's a little thing. It's a little object. There's omega, and here's my favorite little point mass, dm. Okay. Yeah, from here to here, this is gonna be r. So what do we have here? We have that the tiny kinetic energy, I'll just call it dt. Oh. Yeah. It's 1/2 dm v squared. You tell me what to do with v squared.
Omega cross.
Put in something, everything you said is true. Put in something before we do that. What's another way of writing v squared?
Dot V or.
It's a dot product. This is dt equals 1/2 m v dot v. Now this is what kind of animal? A scale. So what can we, let's figure out what to do. So I said that this is 1/2 dm. Okay. How can I write a scalar then? In Einstein's summation notation? VI. Okay. Now, what do we know about V? But we proved earlier that V is our buddy.
Omega cross.
Omega cross R. Now I need to put the ith component in here. So you tell me what I'm gonna put in. VI is
Epsilon.
epsilon.
IJK.
IJK.
Omega J X J X K.
Omega J XK. Yeah, you get XK is really RK, but for the position vector, you always use X. Now, what's the next one have to be? So this is my buddy VI. If you're familiar with Unix and using VI, you don't joke. I think probably most of you have used the VI editor. If you use Unix, there's an editor on it. Unix is actually, there's some wonderful things you can do with Unix. There's an ancient editor, which if you can do, if you use it, the things you can do with it are phenomenal. But it's one of these user hostile programs. So one of my friends would be referred to it as VI, the mark of the beast. And there's just such an evil editor. That's my VI. Okay, so the next VI is
Epsilon IRS.
yeah. What I have to do epsilon. Why does it have to be an I here? Because I'm doing, this is VI, and this first I always refers to basically the different point I'm doing. Now, I can't have a J and a K because then what would I have? I wouldn't have any of my cross terms. Okay, and I have to have the cross terms. So now I have to do RS.
Omega R,
Omega R
excess.
excess. Okay, so I'm gonna rewrite this now. So this is my dt equals 1/2 dm. Okay. Now I wrote this as epsilon, I'll put epsilon I j k. And then I can leave the epsilon here, epsilon I R S. The main thing is that the i's have to be in the same spot. They have to be here or at the end or something. They have to be in the same spot. To use that little theorem we have. And I have omega j x k omega r x s. Now, you tell me what this goes to then.
Delta.
When you have two epsilons and you're summing on one of the indices, that goes to what?
Delta.
Yes, the delta delta minus delta delta. And so then this has to be omega j xk omega r xs. Now, let's see some decorations. Decorate it for me.
The first one will have JR.
Yeah, the first one here, what do we do? The positive term, this J here, matches up with this R here. So this is JR. Then the next one is then we have to be in the KS. And this is KS. Now what happens with the minus term then?
JS.
Yeah, now the J is going to match up with the S. So this is going to be JS. Then that is the last one, which then has to be the J then has to match up with R. KR. Does that make sense? So that's what we get here. So I'm going to get 1/2 dm. Okay. When this acts on here, what does that give me?
Omega J squared.
Yes, and the J has to be the same as this. So this is going to give me omega J squared times xk squared. Why did I put an R here? Why did I call it omega R squared? Or why did I call this one S? You could have. Okay, there's no reason you couldn't now. I leave the J because I know what I'm going to be pulling out. But it's not wrong to have an R here and consider that's not wrong. Minus. So for this true.
Omega J X.
Omega J xj, meaning this one, followed by
Omega K X. Okay.
and so this is going to be omega k xk. Okay. And we're done. Okay. We have to tinker a little bit. Now, what I want to do, only because I know what I want this animal to look like, is I'm going to, first of all, let's figure out what this guy is here. Does that have a name?
R dot R.
That's our dot R, just, this is going to be, right? This is our dot product, this is the R dot R. So this is just going to be our Wed Nov squared. So this is one half dm. Okay. Omega j. I'm going to write it as omega j just because I know where I want this to go. Minus square equals I'm gonna write this as an xj, xk. Uh-oh, getting close to omega j. Omega k. Like that. That makes sense. Now I'm gonna pull out an omega j on the side here. I'm gonna put omega j there. And if I could get rid of, basically, if I could get rid of this guy here. Okay. If I could somehow get rid of this. Maybe have something else in there. I'm getting something that smells like something. What does this start? What is this starting to smell like here? It's not quite there yet. Whenever we had this combination here and then an R here like this,
Why?
when you have the I. The problem is that we had a Kronecker delta here, but in order to make this look like I have to factor out the omega k. I factor out an omega k here. I don't have an omega k here, but is there a fancy schmancy way I can actually do this to get an omega k there?
Right, using negative.
Yeah, I can say that this is really going to be Kronecker JK times
Omega.
omega k, because I'm summing on the k's here. The only thing that's going to survive is the j equals k. So when I do that, I can put this in here, then I can factor out the omega k. So then I can write this as 1/2 dm delta j k r squared minus x j x k omega k omega j. This is my dt. Then I'm going to integrate over this whole thing to get the total kinetic energy. So I'm integrating over this entire object here. Pull out the 1/2 here. Pull out the 1/2 here. I'm going to integrate over the whole object here. So this dm delta j k r squared minus x j x k. Gonna end my bracket here. These are going to be fixed, so I can pull them out of the integral. I'll put them over on the side. Xj here. And this whole thing here is nothing but what? That whole thing here is my moment of inertia tensor, I. And what are going to be my indices here? My indices are
JK.
J and K. This whole thing here is T equals -1/2 I J K omega J K. If I rewrite this as 1/2 omega J X J I J K omega K. Does that have a name?
So matrix.
It's matrix multiplication. It is if I were to write this. And what does that equal? This would really be the jth component of L. Right, because we know we have this. So if I wanted this jth component, what would this be? Remember how would you do with these? This would be the JK omega K. This thing here is this. But as a matrix, this is it, right? This is the dot product. How can I write this as a matrix? I could write this as omega transpose times L. Right? This is the same as this as a matrix. As Kelvin matrices. That makes sense?
Why change?
Why the transpose? How do matrices get multiplied?
Oh, because the first one has to be first.
This is if you were to write it out, this will be 1/2 this one. Times this one here. This. Just this guy here. Okay. Well, what is our L? That's our I times omega. So this gives us the 1/2 omega transpose I omega. Boom. Now we can get kinetic energy as well. And what would happen if I'm in the principal axis? If I is nothing and the principal axis. What does it mean to be tucked in the principal axis? What happens? Your eye is going to be diagonal. What happens here is that I have T because it's 1/2 omega transpose. My eye is this. I just read this. That would work. My omega is this. What is that? So I omega 1, I2 omega 2, I3 omega 3. That gets multiplied by my 1/2 omega 1, omega 2, omega 3. This is just simply 1/2 I1 omega 1 squared. It's 1/2 I2 omega 2 squared. It's 1/2 I3. Great. So when you work with this, what do you want to do? You want to work in the principal axis. In that frame, because like there's going to be a hole like this here. Okay. So what we're going to start tomorrow then is figuring out frequently called Friday, because we're going to assume that Thursday is thin. We're going to quantum mechanically tunnel through it. So what we're going to find out is we're going to actually go to the rotating frame on Friday. And we're going to do a little segue because I want to talk about the Coriolis force and centrifugal force and what happens if you drop a penny in New York State Empire State Building. I guess you don't since it doesn't transfer. What happens if you're in a tall building and drop a penny? But basically, what's going to happen is it doesn't go straight down; it actually gets deflected, even if there's no wind entirely because the So we're going to talk about some of those effects, and we're going to come back and revisit this. We're going to find a way of basically writing our torque equals the LDT in a very, very complicated way. It's going to be referred to as loaded torques. That's how you actually go and analyze a lot of nutritional things, and it turns out to be as bad as you think it's going to be. The whole thing becomes pathological. If we have time, I have to make some that we can get through the central. There's certain topics I have to get to. And one of them is obviously the gravitation. Kepler's laws, we have to draw all Kepler's cells. But I hope to actually maybe do a couple things with the top, because I want you to see the top and I'll explore it. Because it turns out that even, and we're not going to know all this, like in a simple case, in the simple case is pathological. It is an absolutely pathological problem. That top can do really, really complicated things. It just doesn't feel like that. You can get things that go like this. It can do this, and it can go it can do a lot of weird things. John Stahl, when he was alive, said that the company stopped selling that thing because it did too many things that physicists could not explain. And he's probably not wrong, because that thing you can start getting behavior. People would say, why does it do that? Spin. It gets pathological. Have you played that thing before? If you haven't, you want to play that. Set it up with don't have natural gas in it because we don't want to set it on fire. We're going to have everything into it. Okay, everything. Okay, this is going to get pathological remarkably soon.